Welcome to a screencast on an introduction to limiting reactants. Okay, for our next example, we're also going to be using a reaction that involves iron and oxygen, but this time it's the reaction of iron with oxygen to make Fe2O3. And we're going to look at this pictorially, sort of on a molecular or atomic level. And first of all, we need the chemical equation. And when it's written out and balanced, 4 Fe's react with 3 O2s to make 2 Fe2O3s. And with the amounts we are given, here is what that would look like. We have 8 moles of Fe, so each of these blue spheres represents, on an atomic level, 1 atom of Fe. On a molecular level, or on a larger scale level, it would represent a mole of Fe. And then we have 7 moles of O2. Remember that O2 is a diatomic, 2 oxygen atoms bonded together. So we have 7 groupings of pairs of oxygen atoms. So that's 7 moles of O2, or on a smaller scale, 7 molecules of O2. And then we're going to see what happens when these substances combine to make Fe2O3. So see if you can predict what would happen. Move the atoms around so that they end up joining as 2 irons and 3 oxygens stuck together in a unit. And if you do this, let's kind of look at it here with a couple things to note. One is 8 moles of Fe, that's kind of straightforward, but 7 moles of O2 is of course the same as 14 moles of O. You have 7 pairs of oxygen atoms, therefore you have 14 actual atoms, and on a larger scale, 14 moles of O. And so we're going to have to end up with 14 moles of O and 8 moles of Fe. And if we now do this, well, there's an Fe2O3 unit. There's another Fe2O3 unit, and another. And keep track of how many Fe's we are using and how many O2s. And you notice when we get to this point, we've used 8 Fe's, so these are all gone, and we've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of the oxygens, and we've run out of iron. There's no more iron left to react, so the oxygen, there's a little bit of it left over, didn't react with anything. So what's left in our container is going to look like this. This is our products of reaction if it's 100% reacting. So note that when this reaction takes place, what happens is all of the iron gets used up, and there's some leftover O2. And this is the kind of thing that can happen sometimes. What we would say is the iron is the limiting reactant. We ran out of it. It limits how much product can be formed. And we would say that oxygen, O2, is the excess reactant. There's more of it than we need, and it doesn't limit how much product can be formed. So whenever you're dealing with quantitative aspects of chemical reactions, it's important to pay attention to whether or not there's a limiting reactant, because that's going to affect how much product can be formed. So let's go back to the problem we've been dealing with, and let's do the next parts. First of all, how many moles of Fe2O3 could be produced? And it's very important here to note that whenever you do calculations, when you have a limiting reactant, you need to start your calculations with the limiting reactant, because that's what determines how much reaction can take place. So in this case, we have 8 moles of Fe. We know from the chemical reaction that for every 4 moles of Fe that reacts, 2 moles of Fe2O3 can be produced. So that's our stoichiometric conversion factor. That gives us that 4 moles, 4.00 moles of Fe2O3 can be produced. That's our theoretical yield, our maximum yield from this amount of Fe. Now next, to determine how many moles of O2 are left over, what we need to do in this case is, once again, we start with our limiting reactant, 8 moles of Fe, and now we note that 4 moles of Fe require 3 moles of O2 to fully react. And what that means then is that 6 moles of O2 are needed to completely react with the given known amount for 8 moles of Fe. And now if we look at the moles of O2 needed and compare that to the moles of O2 available, and note we have more moles of O2 available than we need, then the difference between those two is going to be our excess. So 7 minus 6 moles is 1 mole of O2. That's our leftover. So our last example for this screencast is a reaction between zinc and hydrochloric acid, and we're asked how much hydrochloric acid is needed to completely react with a given amount of zinc. Notice there's something a little different here. We're determining the volume of a 3 molar hydrochloric acid solution. So this is going to be similar to previous calculations, but there will be the difference of, instead of using a grams and moles calculation or conversion, we'll be using a volume and molarity conversion. So we start with what we have, 25.548 grams of zinc. We need to convert that to moles, and 1 mole of zinc is 65.39 grams. And then from the stoichiometry of the reaction, we know that for every 1 mole of zinc, it requires 2 moles of HCl. And then we're going to have to use our molarity to convert from moles of HCl to liters of HCl solution. And we know that there's 3 moles of HCl in 1 liter of solution. And so we string the calculations one after another. Grams of zinc cancels, moles of zinc cancels, moles of HCl cancels, leaves us with liters of HCl solution, or if you prefer it in milliliters, 260 milliliters of HCl solution. And that's it for this screencast.